We have seen several methods to solve differential equations. We have seen separation of variables. We have seen variation of parameter. And today we will discuss Euler method. Euler method is an approximate method. That means not exact. What we get is not the correct result, the correct solution. We get only a number that is close to the final value. And it is a numerical, not analytic method. That means the result is a number or a series of numbers, but not containing parameters. These are disadvantages, but sometimes we must be happy with that. To solve differential equations. Let me start with a very simple physical experiment. If you take a bicycle and if you ride your bike with speed, say 20 kilometers per hour for 3 hours, then you make 60 kilometers. If you have no problems to understand this, you will have no problems to understand Euler method. This is the heart, this is the core of Euler method, just in different words, in different language. We will call the velocity y derivative, where x, the independent variable, is time, and the distance is y. If we write this as distance is velocity times time, then this is good when the velocity is constant. If the velocity changes, then we consider only a small interval of time, and then we make only a small distance. Instead of difference, we can consider differential. And instead of s, we write y. Instead of velocity, we write the derivative of y. And instead of small interval of time, we need the step size h. And if the step size h is small but finite, then we go back to the difference. So the difference of the dependent variable is approximately the derivative times the interval of time. If we denote the difference as the new value minus the old value, and if we solve the differential equation in the form y derivative is some expression depending on x and y, then we want to express y derivative in terms of x and y using the formula in the differential equation. F at some point xn yn times the step size h. This is slightly confusing. The letter h, the symbol h, has been used for two different meanings. This means hour as the physical unit of time, and this h is not hour. This is some small step of x, some small interval of time. Well, and this is the formula for Newton's method, for Euler's method. We can write it in the form that the new value of y n plus 1, is equal to the old value yn plus the change given by h times function at xn yn. And we want some rule how to increment, how to update the independent variable x. The new value of x, namely xn plus 1, is the old value plus h, the step size. And these are the formulas that are called Euler method. Let me illustrate this for some differential equation. Say y derivative is x squared minus y squared. To start, we need initial condition. So consider the initial condition y at 2 is equal to 1. So we need three things: the differential equation, the initial condition, and the step size h. So consider the step size, say 0.01. Usually the step size h should be a small positive number. The smaller h, the more precise is the result, but the longer time it takes. Now it's a good idea to prepare a table where for different n we write the x values and the y values. Then we evaluate the right hand side, f, and we multiply this f by the step size h. So let's start with index 0, where x0 is 2 and y0 is 1. We just copied the initial condition. And now the computation starts. Knowing x and y, we can evaluate the right hand side of the differential equation. X squared minus y squared is 4, minus 1 is 3. Then we take f, the velocity, and we multiply by h, the small interval of time. H was chosen to be 0.01 times 3 is 0.03. And now we can increment, we can update the point. With index 1, x1 will be x incremented by h. If we take 2 and add 0.01, we get 2.01. And the y value will be incremented by adding h times f, which is the value in the last column. So 1 plus 0.03 is 1.03. And this finishes the first step, and we can go on. If we compute the f, the right hand side, at this point, then we get something like 2.98. This is just approximate value, this is just rounded value. And then, and then when multiplied by 0.01, the increment of y will be 0.0298. And then, in n is 2, xn will be incremented by h to get 0.02. This is exact. And y will be increased by this to get something like 1.06. This is just rounded number. And we can go on, we can evaluate f, multiply by h, we take old x, we add h, we get old y, we add h times f, and so on. This method is quite easy to explain, quite easy to understand, but not good, not efficient enough to use in practice. When we really need some differential equation and we really want to solve it, usually we use a computer with some software which uses much better methods. But the advantage of this method is that it gives a good, new, nice insight into the business of differential equations. And this can be illustrated graphically. If we put the situation in the xy plane, then the initial condition 2, 1 is given by one point in this plane. Then f, the derivative is the slope of the tangent to the graph of the solution. So if we find the slope to be 3, that means it goes this way. Positive, that means increasing, and greater than 1, that means increasing more than 45 degrees. But we follow this direction only for a small time, only just for a small period of time. So we go this direction, but only a small step this way. And then we move to a new point if we increment x and y. And then this new point is this new position, this new point in the xy plane, and the play repeats on and on. At this new point, we evaluate the f, so we find the slope of the tangent. That means we find the direction in which we should go, but we go only for a very small distance given by the time increment by the step size h. So in this way, we get a series of points, and if h is small enough, then these points should approximate the solution of the differential equation. So we get a chain of points, a sequence of points, which, if everything goes well, are close to the graph of the solution to the differential equation.